Imagine dropping a solid stone wall directly across a riverbed. Almost immediately, the water begins dismantling it from two directions at once. The overflow gouges out the soil on the downstream side, while water pushed underground washes away the foundation beneath it. The first mechanism of failure is surface flow. When a river is forced over an obstacle, the water accelerates, converting potential energy into massive kinetic energy. As it crashes down, it creates a turbulent hydraulic jump that violently scours the unprotected riverbed. The second mechanism is entirely invisible. By raising the water level upstream, you create an immense pressure differential. Water is forced down into the permeable soil beneath the structure, creating a pressurized subsoil seepage moving steadily toward the downstream side. This underground flow exerts a hydrostatic force that silently strips away the supporting soil particles from underneath the wall. This process is called piping. It hollows out the foundation until the structure collapses under its own weight. This diagram shows the basic profile of a masonry weir. The main body is the masonry breastwall, which acts as the primary barrier, topped with adjustable crest shutters to regulate the surface level. Notice the completely unshielded base. If you construct this isolated unit directly on a permeable riverbed, the dual forces of surface scouring and subsurface piping will guarantee its destruction. To keep this barrier standing, we have to engineer a complete diversion headwork around it. We must add specific structural components to neutralize both the surface kinetic energy and the subsurface pressure. A modern diversion weir operates as a highly engineered machine. Every concrete slab and driven pile is mathematically placed to control the physics of the river. To defend against the kinetic energy of the overflow, the structure's physical footprint has to extend far beyond the main breastwall. We achieve this by laying down thick, reinforced concrete slabs called impervious floors or aprons on both the upstream and downstream sides. These act as a base plate, armoring the immediate foundation against the rushing water. The downstream apron requires a highly specific geometry. It is built as a sloping glacis, typically graded at a 4-to-1 slope. This precise angle safely receives the accelerating overflow. It forces the violent hydraulic jump to occur on top of solid concrete rather than fragile riverbed soil. This glacis also serves a vital mechanical function. It is poured monolithically with the main pier bodies to provide immense structural rigidity, preventing the formation of cracks caused by eccentric loading. Eccentric loads often come from the constant structural vibrations of railway lines or heavy road traffic operating directly across the top of the barrage. If those vibrations were to fracture the base of the piers, the pressurized subsoil water would immediately penetrate the foundation, compromising the stability of the entire weir. While these extended concrete floors successfully shield the riverbed from kinetic surface energy, they introduce a new problem. They trap the hydrostatic pressure building up directly underneath the concrete. This animated cross-section shows the subsoil water seeking the path of least resistance. Blocked by the main wall above, the seepage travels horizontally, directly beneath the newly laid impervious concrete floor. This trapped seepage generates uplift pressure. The water physically pushes upward against the base of the structure, threatening to dislodge the entire concrete slab. The engineering countermeasure is the installation of cutoff walls and sheet piles. These are driven deep into the riverbed at the upstream and downstream ends, as well as at intermediate toe walls under the main structure. These piles act as subterranean barricades. They artificially force the seepage water to travel a much longer route, down and around each vertical barrier, before it can continue moving horizontally. By extending the total distance the water must travel, friction from the soil absorbs the water's energy. This significantly reduces the residual uplift pressure acting against the bottom of the foundation. This friction also manages the exit gradient. The exit gradient is the speed and upward pressure of the seepage water at the exact point it escapes from under the downstream edge of the concrete. If the exit gradient is too high, the water will vigorously boil up and wash away the soil. The extended sheet pile path slows the water down enough to effectively stop this terminal piping at the downstream toe. We are actively manipulating the invisible geometry of the subsoil, bleeding off the hydrostatic thread before the pressure can fracture the concrete. This schematic illustrates the full layout of the weir components. Notice the extreme outer edges of the diagram, where the rigid concrete foundation meets the natural, erodible riverbed. At the far upstream edge is the launching apron. This is constructed using loose stones or boulders, each weighing at least 30 kilograms, packed together without any rigid mortar joints. If turbulent water begins to dig a scour hole in the riverbed, the loose stones of the launching apron will automatically collapse into that depression. This armors the hole and prevents the erosion from creeping backward toward the critical sheet piles. On the far downstream edge, we face a different mechanical problem. The subterranean seepage water that we slowed down with the sheet piles still has to go somewhere. It must be allowed to escape. This creates a paradox. If we cap the exit completely, the pressure will compound until it shatters the floor. But if we let the water flow out of the soil freely, it takes the fine foundation particles with it. This cross-section details the solution, the inverted filter. It consists of precise layers stacked from the bottom up, starting with medium sand, then coarse sand, small gravels called baudry, standard gravel, and finally heavy ballast. Because the layers increase in permeability from bottom to top, they function together as a one-way valve. The fine sand at the bottom traps the microscopic soil particles in place, while the larger gravel and ballast above allow the depressurized water to freely seep out. These fringing aprons and filters create a controlled, flexible transition zone. They safely bleed off the absolute last remnants of the river's destructive energy before it can undermine the rigid structure. The surface aprons and weirs regulate the flow, but they are not the primary load-bearing structures. A wide river is divided into bays by massive barrage piers. The shallow concrete floors we've built cannot support the immense vertical weight of these piers. This split-screen diagram illustrates how we anchor massive piers. On the left, the standard well foundation method begins by isolating the site with a cofferdam and laying a heavy cutting edge. Workers cast a thick concrete wall, the well siding, on top. Mechanical devices excavate soil from the hollow interior. As earth is removed, the sheer weight of the concrete wall causes the structure to slowly sink into the riverbed. As the well drives deeper, friction builds between the surrounding earth and the exterior walls of the concrete cylinder. Eventually, this skin friction becomes so strong that the well stops sinking under its own weight. To force it down to the final design depth, engineers apply systematic artificial loading. They stack heavy sandbags on a top platform to overcome the friction. Once it hits a stable foundation, the hollow bottom is permanently plugged with compressed concrete. This open excavation works well in shallow conditions. But when depth exceeds 10 meters, hydrostatic pressure forces subsoil water up into the well, making excavation impossible. Engineers then deploy the pneumatic caisson foundation. As shown on the right, this is a fully sealed compartment with lock chambers at the top and an airtight working chamber at the bottom. A compressor continuously pumps air into that bottom working chamber, maintaining an internal atmospheric pressure of up to 3.5 kilograms per square centimeter. That precise, intense air pressure physically pushes back against the groundwater. It neutralizes the hydrostatic threat, creating a completely dry environment where workers can manually dig out the foundation at extreme depths. To keep the critical air seal intact, the system uses two separate lock chambers at the surface. One is dedicated exclusively to the safe transit of the workers, while the second uses winch drums to extract the excavated materials without depressurizing the lower chamber. A functioning diversion headwork is the sum of these specialized defenses, from the inverted filters safely venting seepage at the surface to the highly pressurized caissons anchoring the piers deep below the earth. Building on a permeable foundation demands absolute control over both fluid dynamics and geotechnical mechanics. You have to stabilize the subsoil before you can manipulate the river above it. And it is this very physical framework that makes advanced mathematical modeling, like coastless creep theory, possible in the first place.